So many different combinatorial constructions have been defined, and we don't have time to go through all of them, but I'll do one more called substitution. So these are the ones that we've discussed so far in this lecture: disjoint union, Cartesian product, sequence, power set, and multiset. And again, every one of these has immediate translation to a generating function, and there's many others that are available and still being invented. So I just want to look at one more example called substitution. So again, we have A and B classes, and you have their generating functions. Substitution is written with this operation A, open circle, B in brackets. And what it says is to replace each object in an instance of A with an object from B. And if you do that, you get the compound generating function A of B of Z. And the canonical example of that is called enumeration of 2-3 trees. 2-3 trees are an interesting combinatorial structure that actually have important practical applications in computer science. Again, data structures that are used to implement fast search. And there are trees in which the distance from the root to the bottom is always the same, and every node has exactly 2 or 3 children. So there's only one 2-3 tree with 4 external nodes, but there's 2 with 5 external nodes. It's got to be a 2 node and a 3 node, and the 3 node can be either on the left or the right. There's also 2 with 6 external nodes. You could have 2 3s, or you could have 3 2s, and so forth. So how many 2-3 trees are there with n nodes? And with the substitution operation, it's easy to write down a generating function equation for these types of trees. So that's the generating function equation using substitution. To get a 2-3 tree, what you do is you take each external node and replace it either with a 2 node or a 3 node. Then the distance from the root to the bottom is always the same. So that construction is a way to construct all 2-3 trees. And you want to pick out the coefficient of z to the n in that to find out the number of 2-3 trees with n nodes. But the combinatorial construction immediately gives that OGF equation. Now that's a more complicated kind of OGF equation than we've seen. We can check that it works. From the previous slide, here's the leading term of the generating function. There's 1, 2, 3, and 4. There's 2 of 5 and 6, 3 of 7, and 4 of 8, and so forth. And if you just plug in z squared plus z cubed and collect terms, then you'll see that you get 1, 2, 1, 3, 1, 4, 2 5s, 2 6s, 3 7s, and so forth. So that's an interesting OGF equation that we get from substitution. Now, coefficient asymptotics of this one is extremely difficult, and we'll talk a bit about it later. It actually has oscillations in the leading term, and that's a reference for that, but we'll talk about it later. So just to finish up, I want to give some quotes to it seems so natural to immediately get generating function equations from combinatorial constructions but this approach definitely was controversial for a while. So this is a quote from 1968, not all that long ago, where Berger said that really what combinatorialists should be doing is find a bijection. That's really what we want to know. Why is it that the number of trees of n nodes is exactly the same as the number of binary trees with an external nodes, and so forth? Property is understood better when one constructs a bijection than when one calculates the coefficients of a polynomial whose variables have no particular meaning. And what he said was, the method of generating functions, which has had devastating effects for a century, has fallen into obsolescence for this reason. It's something about variables that have no meaning, and devastating effects, I'm not quite sure what he meant. But what Philippe came to understand, despite this attitude, which was a prevailing attitude in many circles when he was a student, Philippe came to understand in the 80s and 90s that generating functions really are the central objects of the theory of analytic combinatorics. They're not a mere artifact to solve recurrences, as many people believe. They're the central object. We can get generating functions from the symbolic method, and then we can use generating functions to get coefficient asymptotics. So just want to finish with the overview that I started with, that we use the symbolic method to get generating functions, and I just want to point out that we get generating function equations that vary widely in nature. We have all these strange types of equations that arise when we use the symbolic method, and many more. So it's not it's necessarily going to be a challenge to get coefficient asymptotics out of all these types of equations. That's for part 2 of the course. So that's just a look at another construction within the symbolic method, and a comment on the various types of generating functions that we might derive.